All right. Hello, everyone. So for those who don't know me, my name is Brecht de Volder, and I'm a PhD student for already 3 years at the Department of Civil Engineering at Ghent University and KU Leuven, under the supervision of Professor Pieter Rouwens from KU Leuven and Professor Peter Trop from Ghent University. Water waves and floating objects are my daily business, as indicated by the very long title of this presentation. Numerical simulations of an array of floating point absorber wave energy converters using OpenFOAM. Probably not all of you are familiar with the concept of wave energy converters, so I will start with a short introduction about what is wave energy. So here on this slide you see a water wave, which has more or less the shape of a sinusoidal function. And as you all know, waves are causing the up and downward motion of the water level. But that's caused by the motion of water particles. So water particles will follow an elliptic path. So they come back to their original position every time. And that's the reason for the up and downward motion. And because of this motion, waves contain energy. And we want to extract that energy out of the waves to generate electricity. And therefore, we need a special device called a wave energy converter, abbreviated as WEC. And in our research group, we are focusing on the floating point absorber wave energy converter, of which an artist impression is shown here on this slide. So basically, it's a floating object going up and down due to the waves, and that motion will be converted to electricity. So if I'm talking about a WEC, I mean this specific type of a device. So now we are fully warmed up, and how is the rest of my presentation structured? I divided it in 2 parts. The first part is about my research dealing with wave energy. So first I will introduce this problem statement and main goal of this presentation. Thereafter I will talk a short moment about the 2 models I've used. The first one is an experimental model which has been used to validate the second one, a numerical CFD model. And the most interesting part of this presentation is dedicated to discuss the obtained numerical results. But I'm not the only one who is using OpenFOAM in our group, so I will also present the work of 3 other colleagues. And for each part, I will end with a short conclusion. So what's the whole idea of my research of wave energy converters? As you may know, one wave energy converter, one WEC, is not sufficient to capture a significant amount of wave power at a specific location. And therefore, multiple WECs are arranged in a geometrical configuration called an array layout. In such an array, there are interactions between the different devices. So let's make myself clear. If one device is hidden behind another device, it's shielded from the incoming waves, meaning that it will capture less wave energy. But we want to maximize the power output of the complete array. So we have to find the optimal position of each WEC within the array. And that's why the flow field is so important around the devices. And to study that flow field, I'm using the CFD toolbox OpenFOAM, because it solves the 3D viscous flow field around the devices, but also the motion of the devices. So in OpenFOAM, I perform numerical simulations in a numerical wavelength. But then the question is, why do I need CFD? Because we all know that simulations can take a long time. If we have a storm condition and storm waves are propagating towards the WEC, the waves can break on the device and a lot of turbulence will be generated and nonlinear effects become visible. And those 2 things can be resolved with the CFD model compared to other simplified models. So the main goal of this presentation is to show you the problems I faced and the solutions I found in order to validate my CFD model by using experimental data for several test cases. So let's begin with making you familiar with our experimental dataset, the WEC project. And for that project, 25 WECs were installed in a shallow water wave basin. And here you see a picture of a 5x5 WEC array layout. And you immediately notice that only the up and downward motion is considered, so the heave motion. by installing a vertical shaft through the WEC units. But what did we actually measure? First of all, the heave motion, so the up and downward motion of the 25 WECs. Secondly, for the 5 WECs installed in the middle column, we measured the horizontal wave-induced force acting on the devices. And thirdly, around the WECs, several wave gauges were installed to measure the wave field in the wave basin. But I am a numerical guy, and I'm performing simulations in a numerical wave basin. So basically, that's a box filled with water, shown in red, and on top air in blue, with in between the free water surface shown in white. So we are solving the Navier-Stokes equations to get the pressure and the velocity in both the water and air phase. And the position of the free water surface is calculated by the volume fraction, which is a percentage of water within a computational cell. And that's based on the volume of fluid method. So basically what we are using is the interfoam or interdiam foam solver of OpenFOAM. But what else do we need? Right, boundary conditions to generate waves and absorb the waves. So here on the left side, waves are generated and they propagate towards the wave flume. And on the right side, they are absorbed. And therefore we use IH foam, which is an external toolbox for wave generation and absorption. But in order to simulate floating WECs, we have to couple two solvers. The first one is our fluid solver, which calculates pressure and velocity by the Navier-Stokes equations. In this presentation, only laminar solutions will be shown because the Kulicke&Carpenter number was quite low. But if turbulence becomes important, I refer to our recently published paper about the buoyancy modified turbulence model, which will avoid wave damping over the length of the flume, but it will predict the turbulent flow field much better in case wave breaking occurs. But more details later on. And the second solver I'm using is a motion solver, which needs the force acting on the buoys based on the fluid solver, and it will calculate the new position of the buoy, of the WEC. But in order to have a converged solution between the flow field around the devices and the motion of the devices, we need multiple sub-iterations during every time step. And then the next question is, how did we organize the mesh motion in OpenFOAM for multiple WECs? So we are using arbitrary mesh interfaces, AMIs, as indicated by the vertical dashed lines, to create sliding meshes. And those AMIs define a zone of cells around each WEC unit in that zone. And those cells will move according to the heave motion, so the up and downward motion of the WEC inside that zone. But as you see, only the highest and lowest row of cells are expanded or compressed. So only those cells are distorted. And this is to prevent undesirable mesh deformation around the free water surface, so the interface between air and water, to increase the accuracy of the simulations. So the aim of this presentation is to include all the physical processes observed in the experiments in our CFD model. And one of the most tricky things is friction in the experiments. So here on the left, you see a picture of the experimental WEC, while on the right, you see the computational domain in OpenFOAM. And there is a difference between them. The vertical supporting axis is missing here in the mesh, in order to reduce the complexity of the simulation. But we found that that vertical supporting axis is causing friction, and we had to include a linear damper, which is a friction force proportional to the velocity of the WEC. But the whole idea of wave energy converters is to extract energy out of the waves, and therefore we need a power takeoff system, a PTO system. And in the experiments, a Coulomb damper is mimicked. So two Teflon blocks, the white blocks, were pushed against the vertical supporting axis by 4 compression springs. So we also have to include that PTO system in our CFD model, which is a friction force proportional to the horizontal force of which the blocks are pushed against the vertical axis. So now it's time for the most interesting part of this talk, 2 test cases. So remember the 5x5 WEG array? All the WEGs were out of the water except for the 2 WEGs installed in the middle column, WEG 4 and WEG 5. On those 2 WEGs, the linear damper is activated for the vertical supporting axis and the Coulomb damper is activated for the PTO system. And those WEGs are freely floating in the water. And we are generating regular waves, so consecutive waves, all with the same wave height and wave period. On those 2 graphs, the time series of the up and downward motion of the 2 WEGs are presented. So the red line is the experimental data and the dashed black line is the CFD result. And we notice that there is a difference between the 2 lines, in the difference in heave amplitude. So this means that something is missing in our CFD model. So let's make myself clear again. We are generating waves, and those waves are propagating towards the WEGs. But we know that waves will cause a horizontal force pushing against the WEGs. So they will push the WEGs against their supporting axis. So this means that we need a second Coulomb damper, but this time proportional to that horizontal force, that horizontal wave-induced force acting on the WEGs. So let's do a new CFD simulation with a linear damper and the 2 Coulomb dampers, and we get the blue lines. And we notice that the difference in heave amplitude reduces from 60% down to 20%. On the top 2 graphs, those 2, that horizontal wave-induced force, the surge force, is given as a function of time for the experiments and the 2 CFD simulations. And we see 2 things. First of all, the 3 lines are more or less identical. But secondly, that second Coulomb damper doesn't have an influence on that surge force, which makes sense because it's a wave-induced horizontal surge force. On the lower left, you see time series for the surface elevations, so the position of the water level at 3 locations in our wave basin. And the same observations can be made, that the 3 lines are almost identical, that the second Coulomb damper doesn't have an influence on the wave field in our wave basin. On the right, you see a snapshot of our numerical wave basin. And the waves are generated here at right, and they propagate towards the left, where they are absorbed at this boundary. But we see that there is a decreased wave height over here. And that's caused because we increased the aspect ratio of the computational cells in order to speed up the simulations. But by increasing the aspect ratio, the waves were damping out. That's a numerical issue. But that's actually a benefit for us, because we want to avoid wave reflection in our numerical wave tank. So for the second test case, 3 more WEGs are added to the domain. So we have 5 WEGs installed in a line array. And on those 5 WEGs, the linear damper and the 2 Coulomb dampers are activated. And we generate the same regular waves. Here you see the time series of the heave motion of the 5 WEGs for the experimental data, so the red line, and the CFD results shown in blue. And the agreement is quite good, but there are some discrepancies observed. And that's mainly due to model effects in the experiments. So here you see a movie of our numerical wave basin. This time waves are generated on the left, and they propagate towards the right, where they are absorbed. And on this vertical plane, you see the horizontal wave-induced velocity, while on top of the free water surface, contour lines of the surface elevations are shown. And we see that the wave field is quite disturbed around the devices, because we not only have the incident wave field, but the incident waves will reflect against the devices, but they will also radiate around the devices. And the devices itself, they are moving, so they will also generate waves. So it's like a combination of 4 wave fields: incident waves, reflected wave, diffracted waves, and radiated waves. So let's have a closer look to the time series of the surface elevations in our wave basin. Again, red is the experimental data and blue is the CFD result. And we see that there's quite good agreement between them. So our model is more or less validated. So to end, or before ending the first part, I want to show you one of my latest results of a 9 WEC array subjected to regular waves. And I think it's a quite unique simulation because it's a fully 3D viscous flow result of the flow field around 9 WECs. So here you see our numerical wave basin, where again waves are generated on this boundary and they propagate towards the left. And around the array, let's show it here, we see quite complex wave field. But what else do we see? Just behind the array, there's a reduced wave height. And that's because the WECs are extracting energy out of the waves. And that's causing that reduced wave height. And that's what we call a wake. But what I want to say here is that with our numerical model, we have a large freedom regarding the number of WECs, the position of WECs, and the C stage which you want to simulate. And also the resolution of the surface elevations are much higher in the horizontal directions compared to the surface elevation measurements in our experimental wave basin. But I don't mean that experiments are not useful anymore. They are very useful, not only for validation study, but also to get insight in the physics. I mean, you cannot kill all problems with only one weapon. So to conclude the first part, I performed CFD simulations in a numerical wave tank using OpenFOAM. And that model is validated by using experimental data, and I have shown 2 test cases, a 2 WEC array and a 5 WEC array. So further research will include the validation of a larger number of WECs, like the 9 WEC array I showed before. But I also want to analyze the importance of viscous forces and nonlinear effects. And the last thing I want to do is include turbulence modeling, because if storm waves are reaching the array, they will break on the device, and I want to assess impact loads and quantify the survivability of the array in those storm conditions. But you can study more than wave energy in our numerical wave flow. So before I simulated floating objects in our numerical wave basin, I performed a study of wave run-up around a monopile foundation. And those monopiles are used for offshore wind turbines as a foundation structure. So waves are generated on the left and propagate towards the right. And wave run-up is defined as the additional increase or decrease of the water level due to the presence of the monopile. And why is that wave run-up important? Because the maintenance platform on those monopiles shouldn't be destroyed by the waves. And also this simulation is validated by using experimental data, and we found a quite nice agreement between the black line, the experimental data, and the dashed lines, the CFD results. Another interesting application is the simulation of wave breaking. So waves are generated here on the left, and they propagate over a sloping bottom, so the wave height will increase. At a certain moment the waves will start to break. But the tricky thing here is turbulence modeling. Because for wave propagation, so the first zone, we don't need turbulence generation at all. But once the waves are starting to break, we need a fully turbulent solution of the flow field. And that's why we developed our buoyancy modified turbulence model, which will not generate turbulence here in the wave propagation zone, but it will make better predictions of the turbulent flow field at the zones where the waves are breaking. And it's not only me who is performing CFD simulations in our group. So I will now present the work of 3 other colleagues, and I will start with the work of Vincent Rouet, who is sitting there. Maybe raise your hand. That's Vincent. His PhD deals with modeling wave overtopping for a climate-resilient coastal defense system with a very shallow foreshore. So that's typical for the Belgian coastline. And his work is part of the big CRIS project. And the goal of his PhD is to develop a prediction methodology for wave overtopping, as you can see here on the dike in Belgium, to study wave impact forces on sea defenses, and the risk of casualties in building. Because in Belgium, we have the dike, we have the promenade, and we have the buildings next to it. So that's what he wants to study. And therefore he is using numerical models. In the first instance, he will start using OpenFOAM. But the problem with OpenFOAM is that the simulations can take a while. And that's why he is thinking of coupling a faster solver, like Swash for example, at a certain point, and then transfer that information to OpenFOAM. Because Swash is fast, but it cannot handle complex geometries, while OpenFOAM is slower, but you can simulate quite complex geometries. So he is going to couple those two solvers to have an efficient coupling model. And he is going to validate his coupled model by using experimental data, but also field measurements, so real scale or large scale data. And at this moment, he is validating wave transformation and wave forces on coastal structures. And the next step is coupling Swash with OpenFOAM. So here you see an animation of his work. So waves are generated on the left and propagates over the very shallow foreshore. So then we are here. Here you see the typical dike structure in Belgium with a promenade, and this wall is like a fixed wall, it's a front face of the apartment blocks at the coastline. So what's important is to get the flow field right here, because it's like a thin layer of water, and therefore we really need OpenFOAM, but also to study the impact forces of the waves on the buildings. Then the second colleague, Ine van de Beek, who is sitting next to Vincent, she is working on the same project, the same CRIS project, but the focus of her work is on numerical modeling of beach profile dynamics for very shallow foreshores. So if we have storm waves approaching the coast, those storm waves can move a certain amount of sand into the sea. So that's what we call sediment transport. And she will study that using OpenFOAM. So she will perform CFD modeling using the volume of fluid method, but also by using a sediment transport module with dynamic beach profiles. And at this moment, she is trying to implement the sediment transport module in the foam extent package. And then the last colleague is Carlos Arboleda Chavez, who is sitting in the back. And his PhD is about scar protection around offshore monopile foundations in a combined wave and current condition. So if we install a monopile in the seabed, the local flow velocities increases near the seabed due to the presence of the monopile. And those increased velocities will cause erosion of the seabed around the structure. But that's not good for the stability of the wind turbine. So therefore, we are installing stones around the monopile, and we call this scour protection. So what Carlos will study is, first of all, CFD simulations of combined waves and current, but also the CFD modeling of the porous flow inside the scour protection, because that's like a porous media. And therefore, he will also use OpenFOAM and the volume of fluid method and validate that model by using experimental data. And at this moment, he is trying to get the wave field or the wave conditions right at the monopile. So waves are again generated at the left and propagates towards the right. And the blue plane is a free water surface. But the most important thing here is the bottom plane, which shows the magnitude of the velocity near the bottom. And that velocity is very important to study the porous flow inside the scour protection. So to wrap up the second part of this presentation, In our research group, we are performing CFD simulations in a numerical wave basin for several coastal and offshore engineering processes, going from wave energy converters and arrays, wave propagation and wave run-up around monopiles, turbulence modeling for wave breaking, wave overtopping at impact forces on coastal structures, sediment transport in the near zone, and the porous flow modeling inside this cloud protection. So that's it. Thank you.
Any questions?
You mentioned that OpenFOAM is not so fast. Maybe you can tell us how many cells you have in your domain and how many cores you use and how long it takes.
Okay. Well, OpenFOAM is not so fast compared to other simplified models in our case. So that's why I mentioned it's not so fast. The number of cells that we are using is typically in the range about 1 to 2 million. And we run those simulations on, let's say, 12 to 24 cores. But the problem is not the number of cells, it's the time step. Because we have the free surface, we have a Courant limit, and that Courant number should be smaller than 1, and preferably smaller than 0.5. And that's why the simulations are so slow.
Are you aware of the work of Vuko Vukcevic?
The ghost fluid method.
Yes, because he developed a nice solver which might be relevant
Yes.
to speed up your
Yeah.
simulations.
I'm in contact with him, and once the code is released, I will test it for sure,
Yeah.
because it seems promising.
Yes. There's also a way like they have the yearly NUMAP, numerical
Yes.
summer school, and then you can work basically 2 weeks full time with him.
Yeah.
That's also a thing. And then my another question is for the last topic. I think Tian Tang did something similar in the DTU.
Okay.
Because she's working at Light Boston. Otherwise, I'm talking because I'm not in this field, but if you're interested.
Yeah. Yeah, thank you for the information.
Contact with her.
Yeah. Thank you.
What kind of meshes do you use for your
To generate a mesh,
Yeah.
for my wave energy simulations, I'm using block mesh. It was a lot of work to create a mesh, but once I had it, it was really easy to use it. And I know, for example, Vincent, he is using CF mesh. And he is quite happy with that measure.
I have a question as well to get back to the performance issue.
Yeah.
Do you think that the programming language that is used, so OpenFOAM is C++ while Swash is Fortran, does that have a big impact on the performance as well?
I have no idea. I'm not a programmer.
Okay. Any more questions? Nope. Okay. Thank you, Brecht.